What we want to do now in this lecture is actually start talking about the mathematical formalism that goes behind clustering and classification algorithms. In particular, we want to talk about two concepts, which are the ideas of the supervised and unsupervised learning, and how do we frame this in terms of a mathematical structure. So this is, again, from the book by Kutz here, databookuw.com. You have all the code base, lots more lectures, everything for this chapter. And what I'm going to talk about is chapter 5.2, second section of this chapter, and try to introduce this concept of how do we make this mathematical in terms of representation of what supervised and unsupervised learning means. Okay, so those are the two main concepts. And normally when you're doing data science, these are the two large dominant paradigms that are out there. Supervised versus unsupervised. There's also reinforcement learning as well, which is a different type of structure, but we're not going to talk about that here. What we're going to focus on are these two concepts. So they're just like they sound. Supervised learning is where you provide the supervision in terms of what's going to come down to is labels on the data. That's what the supervision means. Unsupervised is you give it no information about the data, and it must discover patterns in the data to exploit and represent back to you. And so what I want to highlight is many of the classical methods, these are not neural net methods, but methods that have been devised for doing these tasks. But I also want to structure it in a mathematical framework so you understand exactly how this thing is formulated mathematically. So let's go here to this idea around supervised and unsupervised. And I want to highlight this with an example. And here's the example. Supervision is all about labels. Labels on that data. So in other words, if you are an expert, you know what the data is, you give a training data set which has labels on it. And so that provides a supervision of what the algorithm is trying to achieve. Unsupervised, you just simply throw the data in and say, find patterns for me. So let me show you a task here. So in these two panels here, what you see here is all a bunch of gray dots. And so your job as an unsupervised learning algorithm, if you write one, is to figure out how would I cluster and classify this data. Now, here, it's pretty easy to see there's one cluster here, one cluster over here. And so what you'd like to do is have an algorithm that, just like our naked eye, can say, oh, look, these look like two distinct clusters. However, when these two clusters come closer together, it's a much more difficult task to figure out if there's even two clusters here at all. Okay? So unsupervised, I give you no information except the location of where the data sits in some state space. And your job is to actually tell me if there's multiple clusters, one cluster, many clusters. So it's a much more challenging task to do unsupervised learning than supervised. Or said another way, your performance metrics are always going to do better in a supervised setting. Okay? Now the supervised setting here is different. What I give you is some data, which is the magenta or green labels. So those gray balls are no longer just gray. I say, here's these magenta balls belong to one class. The green balls belong to another class. And now your job is to take the remaining gray balls and label it as one of those two classes, green or magenta. And you can see here, it really helps because you'd say anything in this cluster here is going to be magenta, over there green. And even when I mix them, you can see what I've done. It's a much harder classification task, but you can see largely that the magenta balls are here and the green lies along this over here. So this is the starting to get to the structure of what we need to understand around supervised and unsupervised. It's all about training labels. Okay? And so what I want to go through in the course of this chapter are some of the dominant leading methods used for both supervised and unsupervised learning so that you have some understanding of how you might do this in a principled fashion. So let's start off with the mathematical structure first. And here's the mathematical formalism that we have to start thinking about. Data lives in some domain. So the idea here is that the domain of the entire data set lives in some D, which is part of an n-dimensional state space, let's say. So that is where all the data can live, and this is, let's say, the real world, and then you collect data from that domain, and your data is called D prime. D prime is a subset, it's contained within D, but there is a gap between D prime and D. So D is the entire world of possibilities. D prime is your subset of data collected from that world. Sometimes there is a big gap between D prime and D. Sometimes D prime is sufficiently rich to span the entire D space. So these things depend a lot upon the data that you collect, and the edge of where D prime and D, wherever those gaps exist, is where machine learning methods tend to fail. Okay? It's very difficult for a machine learning method to extrapolate into a region of data space where it's never seen data from that area. Okay? Oftentimes you're missing data, but the gap between D prime is an interpolation, and in that case, that can work out quite well. So in either case, this is the formal setting. This is where the data lives. This is the space of all possible data. Okay? Now once you have that, we can start going toward the task of what does it mean to do an unsupervised learning task? What does it mean to do a supervised learning task? So let's start off with the unsupervised learning. And here it is. Unsupervised learning is the following. The input is some data, let's call it x of j, living in this n-dimensional space where I have m data points. So I give you a data set. The output are a set of labels. Your job then is to take each one of that data and, for instance, label it. And here what I've shown you is, let's take a scenario where you're trying to label it as one of two classes. So I either get a label of +1 or -1. So the input is this data. Your job is to provide a label of +1 or -1. Okay? No labels are given to you. You have to discover if there's patterns in this data here where it can be exploited to see that there's clusters that it can label these as +1, these as -1. This can be a very challenging task because you've given the algorithm no information about what you're actually looking for or what a +1 is supposed to be or a -1 is supposed to be. Okay? But that is, mathematically, what you're trying to do in unsupervised learning. Input, output, no labels provided. Supervised learning is different. Your input now is all this data that lives m data points, but now I provide labels for all or some of that data. So you can think about this as supervised or sometimes semi-supervised. So the labels come in some subset z prime of all the data z. Okay? So I've given you some data and I've told you this parts of the data, these are 1s, and this part of the data are -1. So I've given you labels associated with this data. Okay? So data with labels. The output of this is to provide labels for all the data. Now you already have some of the labels, so basically you need to provide labels for the rest of the data. So that's the goal here. You provide labeling of the data, and now with that information, you know what you're supposed to be looking for. In other words, you've provided some information about what clusters should be looking like because you've provided labels here for the algorithm to go after and look for features on that data. Okay, so this is the structure then of supervised learning, and you're going to be typically much more successful with supervised learning because you've given the algorithm starting points and information that matters, whereas in the unsupervised it just has to go and try to find structure on its own with some kind of model. We'll talk about some of the models both for supervised and unsupervised learning as we go through the various chapters. So let me give a very concrete example of how do we construct these objects or these features that we need to consider when we think about supervised and unsupervised learning. So I want to start off with the iris example of the last lecture and talk about what are these x, y's, d prime. These are the things that you need to bring to the table to do this machine learning task. So we start off here with x of j, which is your data. This is the features or the state space of this data. And the x of j for the iris data set were things, it was a vector of 4 components, which was the sepal length, sepal width, petal length, petal width. So there are 4 measures. This is essentially the features that you're extracting out of measuring these irises. Okay? So that's x of j. That's what I'm going to give you as data. Now the labels corresponding to those x of j, I'm not only going to give you the measures, but I'm going to tell you it's one of 3 type of irises. A setosa, versicolor, or virginica. Okay? So there's 3 type of irises. There's 4 metrics that you're using. So you have a features and you have up to 3 labels. Okay? So that's the x of j, these are the y's of j. Now, in an unsupervised task, I would just give you all these metrics and say, how many different iris types are there? I wouldn't even tell you if there's 1 iris type, 2 iris types, 3, 4. Part of what the unsupervised learning algorithm would try to do is to determine that there's 3 different objects in there and that it would actually be discovering for you that there's a setosa, versicolor, and a virginica. But this is sort of the data, the x, the y. These are nice examples that are intuitive to show you the kind of things you need for supervision in terms of labels and in terms of the data. Now let's also talk about the domain of this data. So the data space itself, let's call this d prime. This is your data that you collected. In the model that I showed in the last section, there were 150 iris examples. 50 setosa, 50 versicolor, 50 virginica. This is d prime. It is a subset of D, which is the universe of all setosas, all versicolor, all virginicas. Okay? So d prime, what you're hoping for is that d prime, the 50 that I give you, is a very good representation of anything I would see in the real world. Okay? So that's an important part of what you're doing here. Are there gaps between d prime and d? If I've given you a very nice sample of each of these, very good representation of each of these, then there's a very good chance that d prime is going to be sufficient when I do my training algorithm to do a good job in doing classification and clustering of the real world d. So if I pick a new iris somewhere and I measure its petal length, petal width, sepal length, sepal width, it would be very accurate in classifying it as one of these 3 types of irises. Okay? But if I don't give you a very good data set, in other words, I give you 50 very small setosas, and so when it sees a big setosa, it's never seen anything like this, then it will probably mislabel future setosas because I've given you a bad sample draw here. So this is important. So d prime d. And your job partly in collecting data is to try to make d prime be a very good representation of d, which is the real world. More than that, if I've done that, given you that kind of rich data, then this looks more and more like an interpolation task, whereas if I don't give you a very good representation, I'm probably going to have to be doing some extrapolation. Your ability to be successful in data science is going to be greatly improved if you're doing interpolation versus extrapolation. So just that, if you go back to chapter 4, and we talked about regression, we showed what can happen in interpolation and extrapolation. It's very important because it happens here as well. This is why it's so important to give really rich data sets, d prime, that are close to the real world D if you want a good model of clustering in classification. Let's do a simple second example, which is one of the other examples we did in the first section of this chapter, was we looked at dogs and cat pictures. And so let's talk about what these metrics are for supervised and unsupervised learning here. So for dogs and cats, what I gave were images, 64 by 64 images. So in other words, 4,096 pixels. These were black and white photos. So the x of j, or the state space metric that's giving you the data, is 4,096 pixels, or a vector of 4,096. Okay? The labels, y of j, were either 1 or -1 for dog or cat. So I've given you what the data is supposed to be, how big it is, 4,096, the labels, +1, -1, and then we can talk about the domain of the data. So here it is again. D is the domain of all dogs and cats in the universe. So, right? So it's like all possibilities of dogs and cats. D prime is actually the data set I gave you, and that had 80 dogs, 80 cats. So 160 image samples. And so what's interesting about this, right, I'm trying to use 160 dogs and cat pictures, or 80 dogs, 80 cats, to represent all possible dogs and cats that you may ever see. Okay? So again, what I'd like to give you is a good representation of these so that D prime and D, there's very little gap between them, so I don't have to extrapolate into a regime. So for instance, if I were to give you dog pictures and I only gave you golden labs, then D prime would not be a very good representation of D. In other words, the universe of dogs is much broader than golden labs. Okay? So the idea between these 80 dogs is to give you a very large variety of dogs and cats so that the gap between D prime and D is small. Okay? So if I give you any new dog, any new cat from anywhere in the universe of dogs and cats, this would make a nice classifier. So this is the structure for setting up the supervised or unsupervised learning. Again, notice, if I don't give you the labels and I just give you a bunch of images, you'll have to ask the questions, could I discover there is such a concept as a dog or a cat by looking at the data and seeing that there's two unique clusters inside of that data set? So that would be the unsupervised task, whereas the supervised task, I give you some examples of dogs and cats, and I tell you what they are. Your job now is, if I see a new picture of a dog or cat, tell me which one it is. You're going to be much more successful if you have the supervised learning framework than the unsupervised. And then it can get very difficult. I'm giving you here two canonical representations of where clustering and classification really struggle. Okay? So here they are. So what you're looking at here is two labeled data sets, the greens and magenta balls. This would be extremely difficult for an unsupervised algorithm, but even for a supervised algorithm, how do you start drawing classification lines between data that does things like this? Look at this. You have this data, it's kind of wrapped up in each other. You also have one data set inside of the other. So oftentimes when we've been looking at data, you see one cluster on one side, one on the other. You can just draw a line between them. For these kind of data sets, you can't draw lines between these data and these clusters. In fact, you have to start thinking about what's that curve that best separates the two clusters of data. So this becomes challenging because methods for doing this are gonna, we're gonna have to think about what can we do to try to do something like this. Not only that, but even if we think about this as a probability distribution, the data is coming from some probability distribution, look how complex this looks. We're used to thinking about, oh, I did a random distribution which is Gaussian. These don't look Gaussian at all except for the green in here, okay? So this is gonna start giving us troubles down the road, but we're gonna talk about techniques that can basically take these distributions and lift them into higher dimensions to straighten them out, as it were, okay? And we'll go talk about that later, but I want to start now having in your head the thought that there's some very difficult classification tasks that can happen depending upon how the data is distributed in some space that you're looking at it in. Okay? Okay, so just wanted to finish with saying what I try to lay down here is the mathematical architecture you can start thinking about for what supervised versus unsupervised learning is doing. Again, the biggest difference between them is a label. So for supervised learning, I give you some data x of x, and I give you some labels y, and then your job is to say, with any new data I have that's unlabeled, provide me a label y. Okay? And this is from some data, d prime, that lives in some domain d. And in this case, what you're using is the information that's provided to you, which is the labels, to actually be able to label the rest of the data. Whereas in unsupervised, I just give you a bunch of data, and your job is to go figure out, go give me back some labels, where you're going to learn to see if there's any kind of clusters that make sense for this thing to come out and be labeled as something, so that these are patterns that you maybe discover and can show the user, and maybe the user can exploit that for whatever data science purpose that they might have in mind. All that information is here in the book. Databook.uw.com is the website. You can find all the lecture notes here at this PDF file. All the codes and more lectures on the supervised and unsupervised learning are provided there.